Welcome to the Curious Voyager. It's lovely to have you here, wherever you are, whatever hour it happens to be in your corner of the world. Maybe the lamp is still on beside you, throwing a soft little pool of yellow across the ceiling. Maybe there's a blanket pulled up to your chin, or a cup of something warm going cold on the nightstand because you forgot about it the moment your head found the pillow. Maybe you're on a train, or a couch, or the floor, and the day is finally letting go of you. Wherever you are tonight, settle in. You've arrived at the right place to come apart gently at the end of a long day. Tonight I want to tell you about a star, not one of the ones out the window, not one of those enormous burning things 1,000 trillion miles away that took 10,000 years to send you their light. No, tonight's star is much smaller than that. In fact, it's smaller than a grain of salt. You could hold 100 of them on the tip of your finger, if you could hold them at all, which you can't, because each one lives for less than the blink of an eye, and then it's gone. And here is the strange, beautiful, almost unbelievable part. The part I've been turning over in my head for a while now. This tiny star, this speck of a thing, burns hotter than the surface of the sun. And people make them. On purpose. On a table. In a little flask of ordinary water. About 30,000 times every second. That's what tonight is about, a bubble crushed by sound so violently that it flashes with light hotter than the face of our own star. They call it sonoluminescence, which is a long word, so let's break it gently in half. Sono, from sound. Luminescence, giving off light. Sound, into light. That's the whole thing, right there in the name. You push sound into a drop of water, and light comes back out. And when it's a single bubble doing it, held perfectly still, glowing on and on in the middle of a glass, people gave it a nickname that I think is just about perfect. They call it a star in a jar. Now, I want to make you a promise before we go any further. The same promise I always make. We are going to take this slowly. So slowly. There is nowhere to be and nothing to solve. If you drift off somewhere in the middle, if your eyes go heavy and the words start to blur into the sound of my voice and then into nothing at all, that is completely fine. That is, honestly, the whole idea. The bubble will still be here. The sun-hot spark and the supersonic collapse and the little arguments scientists are still having about all of it. None of it is going anywhere. You don't need to remember a single fact. You don't need to understand any of it. There will be no test in the morning. I'll try, as always, not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learnt something on your way to sleep. A fair trade, I think. And before we sink in properly, just a small and quiet thing. If you enjoy these slow journeys, if you'd like more nights like this one, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd guess, so thank you, truly, if you decide to. And to those of you already subscribed, already here, night after night, thank you. It means a great deal. So while you're getting comfortable, tell me, quietly, in your own head, or down in the comments if you like, where in the world are you listening from tonight? What time is it in your corner of the dark? I always love to imagine all of you out there, scattered across the whole turning globe, all of us drifting off to the same strange story. All right, that's enough of that. Let's begin, shall we? Slowly, so, picture a table. An ordinary table in an ordinary room, the kind of place with a slightly buzzing overhead light and a few coffee rings on the paperwork. Nothing about it looks like the birthplace of a star. And that's rather the point of the whole thing, the part that I find so quietly wonderful. Because to make one of these tiny stars, you don't need a mountain-sized machine or a tunnel buried under a border between two countries. You don't need a rocket or a reactor. You need, more or less, a small glass flask of water. That's the beginning of it. Just water. Though not quite any water. The water has to be what they call degassed. And that's a simpler idea than it sounds. You know how a fresh glass of tap water, if you leave it sitting out, will slowly grow a lace of tiny bubbles along the inside of the glass? That's air that was dissolved in the water, quietly coming out of hiding. Ordinary water is full of invisible dissolved gas, the way a fizzy drink is, only far less and far gentler. For our little star, most of that dissolved gas has to be coaxed out first, carefully removed until the water is calm and clear and mostly empty of hidden air. Degassed, still and clean, holding only the smallest, most carefully measured trace of gas. There's a reason for that, and we'll come to it, but for now just picture that flask of very clean, very quiet water, sitting on the table under the buzzing light. Now, glued to the outside of that glass, you'd find a few small discs. These are the clever part. They're called piezoelectric transducers, and I know that's a mouthful, so let's soften it. Piezoelectric is just a word for a certain kind of crystal, a special material that does a rather magical little trick. When you run electricity through it, it changes shape, it squeezes, ever so slightly, and then relaxes, and squeezes again. If you feed it electricity that flickers back and forth very fast, the crystal shivers back and forth just as fast, thousands of times a second. And a shivering crystal, glued to a glass of water, does exactly what you'd expect. It pushes on the water, it sends sound into it. A transducer, really, is just a translator, taking electricity and turning it into sound, the way the little cone in a speaker turns the electricity from your phone into music. And to feed those crystals, you need one more thing: a signal generator and an amplifier, which, again, sounds grander than it is. The signal generator is simply the part that decides the rhythm, the beat, the exact pace of the flickering. And the amplifier is the part that makes it strong, that turns a whisper of an electrical signal into a real, forceful push. Together they tell the crystals, push and release, over and over, at a very particular speed. And that speed matters enormously. The speed they choose sits somewhere between 20 and 40,000 pushes per second. 20 to 40 kilohertz, if you want the proper word for it. Kilohertz just meaning thousands of times per second. And here's a lovely little detail to rest on. That speed is just a touch too fast for you to hear. Human ears, at their very best, can catch sounds up to about 20,000 vibrations a second, and then the world goes quiet to us, even when it isn't. So this sound that is about to crush a bubble into a spark of starlight, is a sound you could never actually hear. It's ultrasound. It sits just past the edge of your hearing, in the silence above the highest note you'll ever know. The whole violent event happens in what is, to your ears, complete and perfect quiet. Isn't that a strange thing to carry towards sleep? A scream too high to hear, folding light out of water, in silence. Now, when those crystals push on the water at just the right pace, something rather beautiful happens inside the flask. The sound doesn't just travel through and leave. It bounces off the walls of the glass and comes back on itself, and the pushes coming in meet the pushes coming back, and they lock together into a standing wave. A standing wave. Hold on to that phrase for a moment, because it's a gentle and important one. Most waves travel. Think of a wave rolling across the sea toward the shore, always moving forward. But a standing wave doesn't go anywhere. It just sits there, trembling in place. Think of a jump rope held by two children, one at each end, swung so it makes that single steady arc in the middle. The rope is moving, oh yes, it's whipping up and down, but the shape of it, that fat curve in the center, stays perfectly still. It stands, that's a standing wave. And inside the flask, the sound sets up exactly that kind of pattern. Places where the water is being squeezed and stretched with tremendous force, and one special place, right in the heart of it, that becomes the stage for everything that follows. That special place has a name. It's called the pressure antinode. And you can just think of it as the belly of the wave, the very middle of that trembling arc, the point where all the pushing and pulling is at its absolute strongest. It's the eye of this quiet storm. And it is exactly there, at that antinode, that we're finally going to place our star. Because now, at last, we add the bubble. A single one. Just one tiny bubble of air, or sometimes a bubble seeded with a special gas we'll talk about later, introduced into the water. And normally, of course, a bubble does the most ordinary thing in the world. It floats up. It rises, wobbling, to the surface, and pops, and is gone. The way the bubbles in a glass of soda race for the top. That's buoyancy. That gentle, constant lift, the same lift that holds a boat up and floats a balloon skyward. Every bubble wants to rise. But this bubble can't, because the sound won't let it. That standing wave, that trembling pattern of pressure, actually pushes back on the bubble, cradles it, holds it in a kind of invisible grip right there at the belly of the wave. There's a proper name for that grip. It's called the acoustic radiation force, which is just a fancy way of saying that sound, when it's strong enough, can push on things, can hold them, can carry them. And this force, this push made of pure sound, is strong enough to fight against the bubble's desire to float away. So the bubble hangs there, suspended, levitating in the middle of the water, in the middle of the antinode, going nowhere. Not touching the glass, not touching the surface, just floating in place, held by a song you cannot hear. A single bubble, levitated by sound. Take a moment with that image. It's one of the loveliest in all of this. A little sphere of air, no bigger than about 5 micrometers across, hanging perfectly still in a glass of water, kept aloft by nothing but a sound too high to reach your ears. 5 micrometers. Let me give you a feel for that, because these numbers only mean something if you can picture them. A micrometer is a millionth of a meter. Impossibly small. A single human hair, one of the ones on your own head, is somewhere around 70 or 80 micrometers thick. So this bubble, this resting bubble, is more than 10 times thinner than one of your hairs. Truly, it is smaller than a grain of salt, smaller than a speck of dust caught in a sunbeam. You would need very good eyes and very good light just to see it sitting there at all, a tiny glinting point suspended in the clear water. That's our star, at rest. That's the seed of the whole thing. And if that were all, if the bubble just hung there quietly forever, this would be a very short and very peaceful story. But of course, the sound doesn't hold still. The sound is a wave, and a wave pushes and pulls, thousands of times a second. And that little bubble, held in its grip, has no choice but to dance to it. So let's slow all the way down now, slower than we've gone yet, and watch a single beat of that dance. One single cycle. Because what happens to this bubble in one flick of the wave in a stretch of time far shorter than you could ever notice, is genuinely one of the most violent things that can happen in a glass of water. And it happens, gently, silently, over and over, without ever disturbing the calm of the room. It begins with a breath. As the sound wave swings into its low-pressure phase, the part of the wave where the water is being gently stretched and pulled apart, the pressure squeezing the bubble suddenly eases. The grip loosens, and the bubble, relieved of the pressure, does what any bubble would do when the squeeze lets up. It swells, it expands, it grows. That stretching phase of the wave even has its own soft name, rarefaction, which simply means the moment when things are pulled thin and loose and open. And in that rarefaction, the bubble drinks it in and balloons outward. It goes from that tiny resting size of about 5 micrometers, and it swells and swells, growing 8, 9, 10 times bigger, out to something like 40 or 50 micrometers across. It puffs up like a tiny lung, taking the deepest breath it can. For a fraction of a beat, our little bubble is fat and round and full. At its very largest, a small glass sphere of gas hanging swollen in the water. And that is the top of the breath. The pause at the height of the inhale. Because now the wave swings the other way. Now comes the push. The sound wave rolls into its high-pressure phase, and all that force that was easing off comes slamming back, and then some. The water clamps down on the swollen bubble from every side at once, squeezing inward, and the bubble, so fat a heartbeat ago, begins to collapse. And I want to choose that word carefully, because it isn't a gentle deflation, like a balloon slowly losing its air over a week on a birthday chair. No, this is a collapse. This is the walls of the bubble caving inward, faster and faster, the whole sphere rushing in on its own center, gathering speed with every fraction of a second. The bubble that had swelled out to 50 micrometers comes crashing back down, not to its resting size, but far, far smaller. Down past 5 micrometers, down and down, crushed to less than half of a single micrometer across. Smaller than it ever was at rest, squeezed to almost nothing. And it happens fast. It happens so fast that this is where the real astonishment begins. In those final moments of the collapse, in the last few billionths of a second, the wall of that bubble is moving inward faster than the speed of sound. Let me say that again, slowly, because it's one of those facts that ought to be whispered. The surface of the bubble, in the last instant before it's crushed, is moving faster than sound itself. Supersonic, somewhere between 1,000 and 1,500 meters every second. That's Mach 1 to Mach 4, several times the speed of sound, the kind of speed we associate with fighter jets, tearing across the sky and cracking the air behind them. Except this isn't a jet. This is the skin of a bubble smaller than a grain of salt. Inside a quiet glass of water on a table, imploding faster than sound in the dead silence of a room where nothing seems to be happening at all. A supersonic implosion in a teacup. That's not poetry, that's just the plain, measured fact of it. And here is why that speed matters so much, why it changes everything. When you crush a gas that fast, that hard, it doesn't have time to do the thing gases normally do, which is to let their heat leak away into their surroundings. Think of a bicycle pump. If you've ever pumped up a tire, you might have felt the pump grow warm in your hands. That's because squeezing a gas heats it up. Push the air into a smaller space, and it gets hotter, always, but with a slow pump, most of that heat has time to escape into the metal and the air around it, so it only ends up a little warm. Now imagine squeezing a gas not over a few slow strokes, but in a few billionths of a second, so fast that not a whisper of the heat has any time at all to escape. All of that squeezing energy has nowhere to go. It all pours straight into the gas itself, into making it hotter and hotter and hotter, with nothing to bleed it away. Scientists have a word for that, for compression so fast that no heat escapes. They call it adiabatic. Nearly adiabatic in this case, which just means very nearly perfectly sealed, very nearly none of the heat getting out. And when you compress a gas that completely, that violently, the temperature and the pressure inside climb to numbers that hardly seem to belong in a glass of water. The pressure inside that collapsing bubble in the final instant is estimated in the thousands of atmospheres, thousands of times the pressure of the air around you right now, all of it crammed into a space smaller than a speck of dust. It's as though the entire weight of a deep, deep ocean were pressed into a single point you couldn't even see. And at the very bottom of that collapse, at the instant of maximum crush, when the bubble is smallest and hottest and most impossibly squeezed, the light comes. A flash, a single spark, born right there at the heart of the crush. That's the flash of Starlight the whole story is named for. The sound has done its work. It has taken a swollen bubble of gas and crushed it supersonically down to nothing, heated it beyond the surface of the sun, and out of that violence comes a tiny burst of light. Sound into light. Right there, on the table. And then, just as quickly, it's over. The bubble has bottomed out, and now it rebounds. Like anything squeezed too hard and too fast, it springs back, re-expanding, bouncing outward again. But it doesn't settle smoothly. It overshoots and shrinks and overshoots again, ringing back and forth, smaller each time, a series of little aftershocks that physicists call afterbounces. And I love the picture they use for it. They say the bubble rings like a struck bell. You know how when you tap a bell, it doesn't just make one clean note and stop. It hums, the note wobbling and fading, ringing itself quiet. That's what the bubble does after its great collapse. It rings, it shivers through a few fading bounces, humming down towards stillness. Except it never quite gets to be still, because the sound wave is already swinging back around into its low-pressure phase again. And the whole thing begins once more. The breath, the swelling out to 50 micrometers, the clamp, the supersonic crush down to less than half a micrometer, the flash, the ringing afterbounces, and again, 20,000, 30,000, 40,000 times every single second. Every one of those cycles a complete tiny cataclysm, a swelling and a supersonic collapse and a spark of light hotter than a star, all of it happening faster than thought, over and over, thousands of times in the space of a single one of your slow, sleepy breaths. And to the eye, from across the room, all of it looks like nothing more than a steady, tiny, unwavering point of light, hanging perfectly still in a glass of water. A little blue-white star, sitting quietly in a jar, humming through 30,000 deaths and rebirths a second, and never once making a sound you could hear. Just sit with that for a moment, before we go on. The stillness of it on the outside and the storm of it on the inside. From where you're lying, it would look so calm. A pinprick of light in clear water, patient and constant, the sort of thing you could watch for an hour and think, how peaceful. And all the while, underneath that calm, a supersonic implosion is happening tens of thousands of times a second. a bubble being crushed to a plasma hotter than the sun and springing back and being crushed again, endlessly, tirelessly, in silence. Beauty and violence, wearing the same quiet face. I find there's something almost restful in that, honestly, the idea that something can be so wild at its heart and so still on its surface. Maybe that's a good thing to carry down towards sleep with you. Now, I've been throwing that phrase around, hotter than the sun, and I don't want you to take it from me on faith, drifting off half believing it's just a bit of nice storytelling. Because it isn't. It's a measured thing. But before we get to those numbers, and to how on earth anyone measured a flash of light that lasts a mere trillionth of a second, let me just pause here on the seam of it, on this quiet ledge between one wonder and the next. Quick reminder, and then we'll carry right on. After years of lying awake with a racing mind, deep sleep finally became possible for me. And now, learning comes easier, the energy is real, the mind stays sharp through the day. Sleeping like a baby, honestly, changed everything. If you want the exact system that made that possible, it's linked in the pinned comments, whenever you might want it. No rush, it'll keep. So, we've watched the bubble breathe and crush and ring over and over in the silent water. We've followed it down through its supersonic collapse to that spark at the very bottom. But we haven't yet really looked at the spark itself. And the spark is where the deepest strangeness lives, where the numbers start to sound less like physics and more like something out of a dream. How long does that flash of light actually last? How hot does that little crushed bubble truly get? And here is the part I find almost tender in its honesty, the part that separates this story from the breathless nonsense you'll find in so many other tellings of it. When it comes to that final flash, to the exact way the light is made in those last impossible picoseconds. The scientists who have spent their whole lives on this, the ones who can build a star on a bench and hold it steady for hours, they still don't entirely agree. They've measured the flash. They've caught a real plasma glowing inside the bubble. And they are still, to this day, quietly arguing about exactly how it shines. But here's where it gets strange. And to get to that, first we have to talk about how anyone measured a burst of light briefer than almost anything else humans have ever timed. A trillionth of a second. Say it slowly, the way you might say it if you were lying there in the dark, half listening. A trillionth of a second. The words are easy enough to let float past. But the thing they point at is so far outside anything your body has ever felt that it barely fits inside a human head at all. Here's one way to hold it. A single second, one ordinary tick of a clock, one slow breath in. Now imagine cutting that second into 1,000 pieces. Each piece is a millisecond, and already you've passed the edge of what you can sense. A hummingbird's wing, a camera's fastest shutter, a blink. Now take just one of those thin slivers and cut it into 1,000 pieces again. That's a microsecond. Then again, 1,000 more. And you're at a nanosecond, the scale at which light itself, the fastest thing there is, crawls forward only about a foot. And you are still not there. You have to cut one more time, 1,000 nanoseconds into 1,000 pieces before you finally arrive at the picosecond. That's where the flash lives, somewhere between about 35 and 250 of those, depending on the day and the water and the exact bubble. The whole event, the whole burst of starlight, opens and closes inside a window so narrow that light barely has time to cross the width of a grain of rice before it's already over. And that, if you let it settle, is a genuinely absurd thing to try to measure. Because think about what measuring really means here. You can't watch it. There's no shutter fast enough to catch it, no eye, no ordinary camera. Nothing you could point at the flask that would ever resolve a flash that brief. The light comes and goes before the fastest everyday instrument has even begun to notice something happened. So how do you time something that ends before your tools can react? How do you put a number on a flicker that would fit tens of thousands of times over inside a single blink? The answer is beautiful, and it's patient, which feels right for a story you're falling asleep to. You don't try to catch the whole flash at once. You give up on that entirely. Instead, you count. Remember, this little bubble isn't flashing once. It's flashing again and again, tens of thousands of times every second, like clockwork, each collapse landing at almost exactly the same moment in the sound wave that drives it. And that regularity, that steadiness, turns out to be the gift that makes everything possible. Because if the flash happens at the same instant in every cycle, then you don't need to see one flash clearly. You only need to catch a single photon from each flash, one tiny particle of light, and note exactly when it arrived relative to the beat of the sound. One photon, one timestamp. Then another cycle, another single photon, another timestamp, and another, and another. Thousands upon thousands of them, each one just a faint dot, each one arriving a hair too early or a hair too late. Do that long enough, and the dots begin to pile up into a shape, a little hill of arrival times. Most photons cluster around the true moment of the flash, a few scatter to either side. And the width of that hill, the spread of when the light actually shows up, that width is the length of the flash. You never saw the flash itself. You reconstructed it, grain by grain, out of pure patience and a great many single specks of light. Physicists call this time correlated single photon counting, which is a mouthful. But the idea underneath it is almost gentle. Listen long enough, one whisper at a time, and the shape of the thing you couldn't see emerges on its own. It was Bradley Barber and Seth Putterman, working at UCLA in the early 1990s, who first pushed this far enough to put a real number on it. And their number was startling. Under about 50 picoseconds, they said. So short that for a while people wondered if the flash might be even briefer than their instruments could resolve. If 50 was just the floor of what they could measure rather than the true length. A flash that might be hiding an even smaller flash inside it. Then, in 1997, Bernd Gompf and his colleagues went at it again with sharper tools, and they measured widths ranging from around 60 up to about 250 picoseconds, shifting depending on how hard the bubble was driven and how much gas it held. Still picoseconds. Still a trillionth of a second class of event, no matter which way you sliced it. The exact number moved around a little, the way real numbers in real experiments always do, but the headline held. This is one of the briefest bursts of light that human beings have ever managed to time in a jar of water on a table. And here's the detail I keep coming back to, the one that I think is quietly the strangest of all. Each of those flashes isn't much light. If you did the accounting, you'd find something like 100,000 to 1,000,000 photons in a single burst. That sounds like a lot until you remember how small a number that really is for light. Your reading lamp is pouring out unfathomably more than that every instant without you thinking about it once. This is a faint thing, a tiny, faint, blue-tinged spark. You could hold the whole flask in your 2 hands and, in a bright room, never know anything was happening inside it at all. And yet, packed into that faint little spark, into those few hundred picoseconds and those few 100,000 photons, is a temperature. A real one, measured, not guessed. And that temperature is where this story stops being merely surprising and starts becoming something you almost don't believe until you look at how carefully they pinned it down. Let's stay with that temperature for a moment. There's no need to rush it, because the number itself won't do the work unless you feel the scale of what you're comparing it to. So let's build that comparison carefully, the way you'd lay 2 photographs side by side and really look at them. The sun, our sun, the one that hangs above us every day, the one that tans skin and bleaches paint and grows every grain of wheat that has ever been put on a table, has a visible surface called the photosphere. That photosphere glows. It glows ferociously. It is around 5,772 Kelvin. That number, 5,772 Kelvin, is a little under 5,500 degrees Celsius, and it is not a metaphor for hot. It is the actual temperature of the light-producing surface of the nearest star to Earth, the source of nearly all the energy that has ever moved through anything living on this planet. And the bubble in the jar, the one not much bigger than a red blood cell at its widest, the one made and unmade by sound, reaches, at the moment of collapse, a temperature that exceeds it. That claim sits a little awkwardly, doesn't it? It sounds like the kind of thing that gets printed on the back of a cereal box for children, one of those science factoids designed more for shock than truth. So it matters enormously to be clear about what we mean, and about how anyone could possibly know, and about how much confidence we ought to have in the number. The way you know the temperature of something you cannot touch and cannot see clearly and cannot insert a thermometer into is through its light. Specifically through its spectrum, through the particular mix of colors, or more precisely the particular mix of wavelengths of electromagnetic radiation that the glowing thing emits. Hot objects emit light in patterns that depend on their temperature in well-understood ways. A poker left in a fire goes dull red, then bright orange, then something approaching white. The color is a temperature reading. This is the principle of blackbody radiation, and it's been thoroughly worked out since the early 20th century. If you can capture the spectrum of the light, measure which wavelengths are there and how bright each one is, you can estimate the temperature of the emitting material. This is what researchers did with the sonoluminescing bubble, or tried to do. And the first thing they found was a puzzle. A maddening, beautiful puzzle that has not entirely been resolved even now. When you look at the light from a sonoluminescing bubble in ordinary water, the spectrum is broadband. That means it doesn't have sharp peaks at specific wavelengths, the way a neon sign does, or the way a sodium lamp does, or the way a spectrum from a known chemical element does. You know that warm orange glow in old streetlights? That's sodium, glowing at very specific wavelengths, 2 narrow lines in the yellow-orange, almost nothing elsewhere. That's what a spectrum from known, excited atoms looks like. Narrow, spiky, readable. The bubble, in water, gives you none of that. What you get instead is a smooth, broad, featureless curve. A continuum. It rises as you move toward shorter wavelengths, brighter and brighter as you push into the ultraviolet end of the spectrum, and then nothing, not because the light stops, but because the water absorbs it. Water is, in fact, remarkably opaque to far ultraviolet light. Not to visible light. Obviously, water is clear to your eyes. But deep in the ultraviolet, at very short wavelengths, water absorbs radiation quite effectively. So any light the bubble produces at those wavelengths never makes it to the detector. The part of the spectrum where the bubble is almost certainly brightest, where the spectrum would be cresting if you could see it, is hidden behind the water itself. This is, depending on your temperament, either infuriating or perfectly poetic. The bubble is hiding its most intense emissions inside the very liquid that surrounds it and defines it. The spectrum we can measure is the tail of something brighter. We see the edge of the fire, not the fire's center. The shape of the tail is still informative. A broadband continuum rising into the ultraviolet is consistent with a very hot, dense source, something in the class of a thermal emitter, whether that's a classical hotspot radiating like a blackbody or a plasma radiating through other mechanisms. Temperature estimates made by fitting the observable part of the spectrum have commonly come out in the range of 10,000 to 20,000 Kelvin. Some analyses push higher. The exact answer depends on assumptions about the emission mechanism. And that mechanism, as we'll come to in a little while, is genuinely disputed. But for now, let's stay with the broadband continuum and the ultraviolet and what they together suggest. Something inside that collapsing bubble at the moment of maximum compression is emitting light with the character of a very hot source, hotter, by the numbers, than the photosphere of the sun. Not by a little, by a factor of roughly 2 to 3 at the conservative end of the estimates. In water. In a jar. Driven by sound. The challenge with the broadband spectrum is precisely that its featurelessness makes it hard to read. A spectrum with sharp lines tells you which atoms are present and in what state. Narrow sodium lines means sodium atoms emitting from a particular energy level. Hydrogen lines, helium lines, calcium lines, they're like fingerprints. Unambiguous, you look at the fingerprint and you know who was there and how excited they were. A smooth continuum, by contrast, is harder to decode. It could be a black-body radiator, an object so hot and dense that individual atomic emissions blur together into a thermal glow. It could be Bremsstrahlung, a word from German meaning breaking radiation, the light emitted when charged particles, like electrons, are decelerated rapidly, as happens in a hot plasma. It could be a combination of both. Without sharp spectral lines to anchor you, it is harder to say exactly what's producing it and precisely how hot it really is. Which is why a paper published in the journal Nature in 2005 changed the conversation quite significantly. The researchers were David J. Flannigan and Kenneth S. Suslick, working at the University of Illinois. Suslick had spent years studying the chemistry driven by cavitation and sonoluminescence, a field called sonochemistry, and his group had developed an unusual approach to the bubble problem. Instead of using water as the host liquid, they used concentrated sulfuric acid. This sounds alarming, and in a practical sense, sulfuric acid is not the most comfortable thing to work with. But as a host for sonoluminescence, it has properties that make it scientifically remarkable. The bubble in sulfuric acid is far brighter than in water, dramatically brighter. And crucially, the emission extends further into the visible spectrum in ways that carry more information. The acidic environment changes what the bubble contains and what chemistry is happening inside. But the basic acoustic mechanism is the same: sound waves, a trapped bubble, violent collapse. And what Flannigan and Suslick found when they analysed the spectrum from that brighter bubble was something the water experiments could not clearly show: spectral lines. Sharp, identifiable, discrete lines sitting on top of the continuum. each one a fingerprint from a specific atom or ion in a specific excited state. Argon lines. Specifically, lines from ionized argon, argon atoms that had lost an electron, written in spectroscopic notation as R+ or R2. And lines from oxygen atoms and ions in excited states as well. These are not the signatures of a merely hot gas. These are the signatures of a plasma. A plasma is a state of matter in which the temperatures are high enough that electrons are stripped away from their parent atoms entirely, creating a soup of positively charged ions and free electrons. It is the fourth state of matter, beyond solid, liquid, and gas, and it is the state in which the sun shines, in which stars shine, in which lightning bolts shine, briefly, in their channels of superheated air. The bubble, at the moment of collapse, Flannigan and Suslick found, is briefly a plasma, not a metaphor, not a loose comparison. An actual, measured plasma, its presence attested to by the specific spectral lines of ionized atoms caught emitting light at the instant of maximum compression, and the temperature they derived from those spectral lines, from the ratios of emission intensities, from the positions of the lines, from the physics of how excited atomic states behave, was approximately 15,000 Kelvin. 15,000 Kelvin in a bubble that at that moment had a radius of less than half a micrometer, a radius smaller than the wavelength of visible light itself. To be precise about that comparison again, the Sun's photosphere, the glowing surface of our star, sits at 5,772 Kelvin. The bubble sits at 15,000 Kelvin, by Flannigan and Suslick's measurement, that is roughly 2.5 times hotter than the Sun's surface. Not a poetic approximation. A ratio derived from spectroscopic measurements published in a peer-reviewed journal after careful, detailed analysis. And the 15,000 Kelvin is not necessarily the highest temperature present in the bubble. This is one of the genuinely open questions, the ones the title of this video promises to acknowledge honestly, and we will come to it in more detail later. But for now, what spectroscopy gives you is the temperature of the light-emitting surface of the emitting region. If the core of the bubble is optically thick, if it's so dense that light can't easily escape from its very center, then the measured temperature is the temperature of the outer part of the plasma, not the innermost, hottest point. The core could be hotter. How much hotter is a real, active question. But 15,000 Kelvin is what the data directly show. 15,000 Kelvin in a tiny bubble in a flask, on demand, tens of thousands of times a second, built from nothing more than sound and liquid and a few $100s worth of electronic equipment on a lab bench. The word plasma deserves a moment of care, because it's worth knowing what it means to the people measuring it, not just as a general concept. In everyday speech, plasma sometimes means the pale yellowish liquid that blood cells float in. That's a different use of the word, borrowed by medical science in the early 20th century from the physical chemistry sense. In physics, a plasma is ionized matter, matter hot enough that electrons have been knocked loose from atoms and roam freely. This is the state of the interior of stars. It's the state of a lightning bolt for its brief existence. It's the state of the gas inside a fluorescent tube while it's conducting electricity. It is not a state you normally encounter in a jar of liquid at room temperature, driven by nothing more forceful than a small loudspeaker glued to the outside of the glass. And yet there it is. The ionized argon is the key. The R+ lines in Flannigan and Suslick spectrum are, in a very direct physical sense, the atom saying, "I was hot enough to lose an electron." The first ionization energy of argon, the energy you need to provide to strip one electron from a neutral argon atom, is about 15.7 electron volts. At thermal equilibrium, the fraction of atoms that are ionized at a given temperature is described by the Sascha equation, which relates temperature to the balance between ionization and recombination. At 15,000 Kelvin, a small but measurable fraction of argon atoms are ionized. That's consistent with what Flannigan and Suslick saw. The numbers fit. The spectral lines appeared where theory predicted they should appear if the temperature was in that range. This is not a story built on a single dramatic claim. It is a triangulated result, the shape of the continuum, the presence and intensity of specific ionization lines, the predictions of plasma physics, all pointing at the same place. Still, let's hold on to the word approximately. 15,000 Kelvin. At the concentrations and conditions of those experiments, different concentrations, different driving pressures, different dissolved gases, you get different numbers. The water-based bubble is harder to read precisely because of the UV absorption problem. The sulfuric acid result gives us a cleaner view into a brighter bubble, but it's not identical to the water case. Science builds a picture from multiple angles, and the angles don't always produce a single sharp point. They produce a region, a range, a best estimate with honest uncertainty around it. What we can say with real confidence is this: temperatures in the bubble during collapse genuinely and measurably exceed the surface temperature of the Sun. The spectroscopic evidence from Flannigan and Suslick's 2005 Nature paper provides direct, published, peer-reviewed support for plasma formation at temperatures around 15,000 Kelvin. And the true peak temperature at the hidden, optically thick core may be higher than that, possibly much higher, though by exactly how much remains an open question that active researchers are still working on. There is something quietly wonderful about that state of affairs. Not wonderful in a vague, hand-wavy way. Wonderful in the specific sense that this field of science has the character of a mystery novel where the crime is known, most of the suspects have been eliminated, but the exact last step, who precisely, in the final picoseconds, lit the match, is still being argued over. Not because researchers are careless or confused, because the thing they're trying to look at is hidden inside a bubble smaller than a wavelength of light, at a temperature plasma state, for less time than it takes light to cross a human hair. It is, in a very real sense, one of the hardest things to look directly at that physics has ever tried to study. Now, go back for a moment to the clock steadiness. Because when you first describe sonoluminescence to someone, the natural image is of something chaotic, a violent thing, a bubble slamming shut in fluid. Surely that ought to produce erratic, unpredictable flashes, a stutter, a sputter, an irregular spray of light correlated only loosely with the sound driving it. That was the character of the original multi-bubble case from Frenzel and Schultes in 1934. A cloud of bubbles, all different sizes, all collapsing at slightly different moments, producing a diffuse, jittery, bluish glow. Interesting, but incoherent, hard to study, hard to measure, hard to pin down. The single bubble case Gaitan achieved in 1989 and 1990 was completely different in character. One bubble, held at the pressure antinode, driven by a single stable acoustic frequency. And what emerged from those experiments, and what was confirmed and measured with increasing precision in the years that followed, was a flash that was astonishingly regular in time. The flash does not come at some random moment during the acoustic cycle. It comes at a specific phase of the cycle, synchronized to the driving sound field. The bubble expands during the rarefaction phase, collapses during the compression phase, and the light pulse arrives at the same point in the compression every single time. Over and over, 20,000 times a second, 30,000 times a second, 40,000 times a second, depending on the drive frequency. And the timing jitter, the cycle-to-cycle variation in when exactly the flash arrives relative to the driving acoustic phase, is itself at the picosecond level. This is the number that surprised researchers. Not just that the flashes are brief, that they are brief and nearly perfectly periodic. The bubble is not just collapsing and glowing. It is collapsing and glowing on schedule to within trillionths of a second, cycle after cycle, for as long as the acoustic field is maintained. This regularity was not guaranteed by theory. It emerged from the physics of a single stable trapped bubble in a well-controlled acoustic field, and it was the property that transformed sonoluminescence from a curiosity into something measurable. You cannot time a flash reliably if the flash arrives at a random moment. You cannot accumulate signal from many cycles if the cycles don't line up. The synchronization is what opened the door to the photon counting measurements, to the spectroscopy, to everything that followed. The technique that let Barber and Putterman in the early 90s constrain the flash duration to under about 50 picoseconds, and that Bernd Gompf and colleagues refined in 1997 to map out widths between 60 and 250 picoseconds, is called time-correlated single photon counting. It is a method borrowed from the laser physics community, used to measure the duration of very fast light events by building up a statistical picture from many individual detected photons. Here is how the logic works. You cannot photograph a picosecond flash directly. You do not have a camera with a shutter that fast. What you can do is set up a detector that registers the arrival of individual photons one at a time, and record very precisely when each one arrives relative to a reference signal, in this case, the acoustic drive frequency. The same electronic signal running through the piezoelectric transducers. In any given cycle, the detector might register one photon, or none. Most cycles, none. Occasionally one. Very rarely two. You record the time difference between the drive reference and the detected photon over thousands upon thousands of cycles. And then you look at the distribution of those time differences. If the flash is a brief pulse synchronized to the drive, all the detected photons will arrive within a narrow window, clustering around the same moment in the cycle. The width of that cluster gives you the width of the flash, convolved with the timing resolution of your detector. With careful calibration and correction, you extract the flash duration. It is patient work. You are building a portrait of a trillionth of a second event from thousands of single photon snapshots, each from a separate cycle, assembled the way a mosaic is assembled. One tile at a time, each tile a single detected photon at a measured time. The flash is real. The synchronization is real. The regularity of the bubble is what makes the mosaic assembling possible at all. Gompf and colleagues' 1997 result is notable for showing that the flash width is not a single fixed number. It varies. At lower acoustic driving amplitudes, the flash is narrower. Push the driving amplitude higher, drive the bubble harder, and the flash broadens. Somewhere in the range of 60 to 250 picoseconds, depending on conditions. This variation itself carries information about the physics inside the bubble. A flash that broadens with drive amplitude is telling you something about how the emitting region evolves as the collapse becomes more violent. It's another data point in the argument about what mechanism is producing the light. 100,000 to 1,000,000 photons per flash, 60 to 250 picoseconds, synchronized to the drive to within picoseconds, cycle after cycle. Let's sit with the smallness of that for a moment. A picosecond is 1/1,000,000,000 of a second, 1 divided by 1,000,000,000,000. If a single second were stretched out to the length of the diameter of the Earth, roughly 12,700 kilometers, a single picosecond in that scaling would be about 12.5 millimeters, less than the diameter of a large grape. The flash, in that scaling, spans the distance of somewhere between 1 and 3 grapes, set against the full diameter of the Earth. And in that grape-sized sliver of time, at the center of a bubble smaller than most bacteria, a plasma briefly exists at temperatures higher than the surface of the sun. It doesn't stay, it cannot stay, it is transient by necessity. The bubble then bounces, expands again slightly in a series of smaller afterbounces, ringing like a bell struck once and allowed to vibrate, before the next acoustic cycle comes along and the whole process repeats. Expand, collapse, flash, bounce, expand again and again. The bubble is a clock, and the light is its chime. Now let's talk about what the spectrum is actually telling us, or more precisely, what it is telling us, and where it stops being able to say anything clearly. The continuous, featureless spectrum is consistent with a thermal emitter, something that glows because it is hot, the way a piece of metal glows when heated in a forge, not because specific atomic transitions are emitting at specific wavelengths. But a continuous spectrum can also emerge from a plasma emitting through Bremsstrahlung, or through a combination of thermal and non-thermal processes, or through a dense enough plasma that individual line emissions are broadened and blended together into a continuum. The spectrum shape alone does not tell you which of these it is. This is why the Flannigan and Suslick result in sulfuric acid was so valuable. The ionic emission lines, the R+ and O+ features, were something the spectrum in water could not show clearly. Water's UV absorption removed the region where such lines would most clearly appear in the water-based case. The sulfuric acid environment, different in its chemistry and optical properties, let those lines through. But here's the complication you have to carry with you. Concentrated sulfuric acid is not degassed water. The bubble in sulfuric acid is brighter, its spectrum richer in information, but it's not necessarily a perfect stand-in for the more common water case. The temperatures inferred from the acid experiments, that approximately 15,000 Kelvin figure, are unambiguous for those conditions. Whether the water bubble reaches similar or different temperatures is a related but separate question, and the answer is harder to get because the water absorbs the most informative part of the emission. This is the honest texture of experimental physics. You design an experiment that can answer a question, but the answer is then specific to those experimental conditions. Another set of conditions requires another experiment. The knowledge builds in pieces, each piece real, each piece sitting in a larger, still incomplete picture. What the pieces together suggest is something like this. The collapsing bubble compresses its gas, its plasma, by the end, to temperatures that genuinely, measurably exceed the sun's photospheric temperature. The spectroscopic evidence makes this credible, not merely claimed. The emission from the observable surface of the emitting region is around 15,000 Kelvin in the best characterized experiments. The true core temperature, the center of the plasma at the moment of maximum compression, is hidden behind the optical thickness of the plasma itself, behind the UV absorbing water, and behind the picosecond timescale that limits how long you have to look. What the core temperature actually is remains, as of this writing, an open question in the field. And that openness is not a failure of the science, it's the frontier. The thing that is still being worked on, written about, argued over in publications and conferences. Sonoluminescence is not a solved problem tucked away in a textbook. It is an ongoing research topic, and the genuine, bounded uncertainty at its center about what exactly happens in the last bright picoseconds, about whether the emission is purely thermal or involves other plasma processes, about what the true core temperature might be, is part of what makes it alive. Here's something to close this chapter of the story on. Something I find quietly lovely about how the spectrum works as a piece of evidence. The water absorbing the far ultraviolet is not just an inconvenience for researchers, it's part of the physical reality of the system. When the bubble emits its ultraviolet light, and that light is absorbed by the surrounding water, the energy goes somewhere. It goes into the water as heat. The bubble is not just emitting light, it is depositing energy into the liquid around it, ultraviolet radiation absorbed and converted to thermal motion, warming the water molecule by molecule. On the scale of a single bubble, this is negligible. The flask stays cold. But the physics of that absorption is real, and it's a reminder that the bubble and the liquid are not independent. They are coupled. The bubble lives inside the liquid. The liquid shapes what we can see of the bubble. The bubble's light shapes, in its tiny way, the liquid around it. The flash reaches out into the water and vanishes. We catch only what the water lets through. And what it lets through is enough to tell us that something remarkable is happening, enough to name a temperature, to identify a plasma, to measure a duration. But the innermost heat, the true peak of what happens at the center of the collapse, stays hidden for now behind the very medium in which the whole phenomenon lives. That's where the spectrum leaves us. At the edge of a fire, looking in, with the certain knowledge that we are seeing the bright rim of something brighter still at the center, and with the honest admission that we can't yet see the center clearly. And this is a good place to begin asking the next question. Not about the temperature, we've established that as best we can from the evidence. The next question is about the mechanism. Not what temperature, but how. How does sound compressing a gas into a plasma produce a burst of light? What physical process, in those last bright picoseconds, is the one making the photons? Because it turns out that knowing the temperature, knowing the spectrum, knowing that a plasma is there, none of that fully answers the how. There are competing ideas, each supported by some of the evidence and challenged by other parts of it, and the argument between them is genuine and ongoing. The bubble is hot. The bubble glows. But exactly which process is doing the glowing, in what proportion, by what path, that is the open question at the heart of the field. And it is exactly the question the title of this video promises not to brush past, not to resolve falsely, but to put on the table in all its honest complexity. We'll go there next. But first, let's follow the story back to where the bubble itself came from, to the people and the places and the experiments that built this whole strange, beautiful phenomenon from the beginning. Because there is a human story underneath the physics, as there always is, and it begins not in the 1990s, but decades earlier, in a sonar laboratory in Cologne, with a jar of photographic developer fluid and a mystery that nobody went looking for. So let's begin there, with the bubble itself, and what fills it. Because there is something inside that tiny collapsing sphere that turns out to matter enormously. Something that shaped the whole story of why some bubbles glow and others don't. Why some experiments produced brilliant, reliable flashes and others produced almost nothing. Why a bubble in ordinary air behaves so differently from a bubble in pure nitrogen or pure oxygen or a careful mixture of the two. It comes down to the gas. And specifically, it comes down to a family of gases that most people have heard of but rarely think about. The noble gases, the chemical loners of the periodic table. Argon, xenon, neon, krypton, the gases that sit at the far right of the table, reluctant to react with anything, chemically aloof, in a way that turns out to be exactly the right character for a bubble that needs to survive tens of thousands of violent collapses in a row. Here is the thing about argon and why it matters to a glowing bubble. Argon is inert. Genuinely, stubbornly, chemically inert. At the temperatures ordinary matter encounters in everyday life, argon does not react with nitrogen, or oxygen, or water, or almost anything else. It simply sits there, composed and unmoved, while the world around it engages in chemistry. And inside a collapsing sonoluminescing bubble, where temperatures briefly reach thousands of degrees, where pressures are enormous, where the gas is compressed almost too fast for heat to escape, that inertness is not a minor detail, it is the whole story. Think about what happens to the other gases. Nitrogen, oxygen. The molecules that make up most of the air around you right now, seeping gently through your window or circulating through the ventilation wherever you are lying down tonight. When those molecules are driven into a collapsing bubble and subjected to the catastrophic heat of a supersonic implosion, they don't just get hot, they react. The nitrogen molecule, that tightly bonded pair of nitrogen atoms, can be broken apart at high enough temperatures, dissociated, in the language of chemistry, split into its individual atoms. The oxygen does the same. And once dissociated, those atoms can combine with water molecules, or with each other, or with dissolved species in the surrounding liquid, forming new molecules, hydroxyl radicals. Nitric oxide, a scattered assortment of chemical products that find their way out of the bubble and dissolve into the surrounding water. And here is the consequence of that, and it is a beautiful and subtle consequence. Every time the bubble collapses and the reactive gases inside it are dissociated and their products dissolve away, the reactive fraction of the bubble's contents shrinks a little. The nitrogen and oxygen are very slowly being consumed by the very violence they are subjected to. Eaten, you might say, by the collapse itself. But the argon is not. The argon just sits there through collapse after collapse, accumulating as a fraction of the bubble's gas, simply because it has nowhere to go. It cannot react. It cannot dissolve away as a chemical product. It cannot be destroyed. And so, over many thousands of acoustic cycles, remember, the bubble collapses 20 or 30,000 times per second, so many thousands of cycles can pass in less than a second, the bubble's interior composition shifts. The reactive gases are slowly removed. The inert argon remains. What started as an air bubble gradually becomes, effectively, an argon bubble, washed clean of everything reactive, left with only the composed, impervious noble gas. This is the argon rectification hypothesis, and it was worked out in the mid-1990s by a group of physicists and fluid dynamicists, Detlef Lohse, Michael Brenner, and Sascha Hilgenfeldt among them, who were trying to understand not just what a sonoluminescing bubble does, but what it is, what it's made of, and why it behaves with such remarkable stability over time. The word rectification here is worth sitting with for a moment. In electronics, a rectifier is a component that allows current to flow in one direction and blocks it in the other. It converts alternating current, which swings back and forth, into direct current, which flows one way. The argon rectification process does something analogous. Gas moves into the bubble during the expansion phase, and gas moves out of the bubble or is consumed during the collapse phase. But these two flows are not symmetric. The reactive gases exit more readily than they enter. They are transformed in the hot collapse and expelled as dissolved reaction products. The argon, being inert, cannot exit that way. So the net effect over many cycles is a one-way accumulation of argon inside the bubble. The bubble rectifies its own chemistry. The result is elegant. A bubble that started as an ordinary air bubble with roughly 78% nitrogen and 21% oxygen and 1% argon gradually becomes dominated by that 1%. The majority is slowly removed by the violence of the collapse itself. The minority, the inert, glowing argon, is what's left, and this is why the experiments so reliably use argon or xenon when they want a bright and stable sonoluminescing bubble. Not because air doesn't work. Air works. Air was there at the beginning of the field in the earliest experiments, and it produces sonoluminescence quite reliably. But it works precisely because of its argon content, that 1% that sits quietly at the right end of the periodic table. If you took air and removed the argon, if you could make nitrogen-oxygen air with no noble gas at all, the results would be far dimmer, far less stable, far harder to sustain. The glow is coming from the fraction most people don't notice. The fraction that does nothing, reacts with nothing, and survives everything. There is something almost poetic about that. The loudest, most violent, most dramatic process in a kitchen bench experiment, a supersonic implosion, a plasma flash, a temperature exceeding the surface of the sun, and the reason it works, the reason it sustains, is the quietest gas in the room, the one that just sits there. And xenon, for what it's worth, is even more dramatic in this role. Xenon is heavier than argon, a larger atom, and a sonoluminescing bubble seeded with xenon is brighter still. The noble gases generally enhance the emission, with the heavier, more polarizable atoms tending to produce more vivid results. But argon is the workhorse, the one most commonly used in laboratory settings, the one that nature itself provides in the air, that one quiet percent. Now, there are other conditions that turn out to matter, and one of them is genuinely counterintuitive. Cold water. You might expect that hotter water would produce more energetic bubbles, more violent collapses, more light. Heat means energy, and energy means more of everything. That is the intuition most people carry. But the experiments say something different, and they say it quite clearly. Colder water produces brighter sonoluminescence. Water near freezing, close to 0 degrees Celsius, nearly ice, gives far stronger flashes than warm water, or water at room temperature, or anything approaching the warmth of a comfortable bath. The colder the better, up to a point. And this seems backward at first, wrong, like a machine that runs faster when you cool it down. The reason comes back to the physics of the collapse, and particularly to the adiabatic compression that heats the gas. When the bubble collapses, the gas inside is compressed quickly, so quickly that heat doesn't have much time to escape through the bubble wall before the collapse is over. The compression is nearly adiabatic, as the physicists say, and the temperature reached depends partly on the ratio of the gas's initial temperature to its final density, on how much energy is concentrated into how small a space in how short a time. But the liquid surrounding the bubble also matters. Cold water has different physical properties from warm water, different viscosity, different surface tension, different vapor pressure, and the vapor pressure is particularly important. Warm water evaporates more readily. There is more water vapor in the bubble's immediate environment in warm conditions, and that vapor can soften the collapse, cushioning the final implosion with molecules that absorb energy without contributing to the adiabatic compression in the same way. Cold water evaporates less. The bubble's environment is cleaner, drier, and the collapse can proceed more fully, more completely, more violently, reaching higher temperatures at the moment of minimum radius. So the cold water shines brighter because the cold water gets out of the way. Because it contributes less interference to the final terrible moments of the collapse. The colder the medium, the cleaner the implosion, and the more extreme the conditions at the center. It is one of those results that feels strange until you understand it, and then feels inevitable. The same logic that makes a clear night colder than a cloudy one, less interference from above, applies in a radically different physical regime to a bubble collapsing in water at ultrasonic frequencies. The stable regime for a well-behaved sonoluminescing bubble is also narrow in terms of the driving pressure. The acoustic wave that traps and drives the bubble needs to be within a certain range, roughly 1.2 to 1.5 atmospheres of acoustic amplitude, to sustain stable, single bubble emission. Too gentle and the collapse is too mild, the temperatures too low, the light too faint or absent. Too strong and the bubble becomes unstable, splits, or is destroyed. The sweet spot is not wide. The conditions have to be tuned, which is partly what makes this a laboratory phenomenon rather than something that happens accidentally in your plumbing, even though your plumbing does cavitate. Even though bubbles do collapse in fast-moving water, just not under the precise, sustained, single-frequency conditions that produce a steady, single, glowing bubble. And there has to be enough dissolved gas in the water, but not too much. The water used in SBSL experiments is typically degassed, treated to remove most of the dissolved air, and then carefully reseeded with the desired noble gas at a controlled partial pressure. Too much dissolved gas and the bubble grows unstable, too little and it cannot sustain itself. The apparatus is delicate. It took years of careful work to understand which parameters controlled what, and why the same experiment done slightly differently could produce either a beautiful sustained glow or nothing at all. All of this, the argon story, the noble gas chemistry, the counterintuitive cold water result, the careful tuning of the stable regime, emerged from the intensive scientific work of the 1990s. But the phenomenon itself is older than all of that. Older than the equipment used to characterize it, older than the theoretical frameworks developed to explain it, older even than the ability to trap a single bubble and study it in isolation. The beginning is in 1934. Cologne, Germany, a laboratory at the University of Cologne, where two researchers, Hermann Frenzel and Heinrich Schultes, were working on practical problems related to sonar and ultrasound. Ultrasonic transducers, devices that convert electrical signals into sound waves at frequencies above human hearing, were being studied for their potential applications in imaging, in materials processing, in the behavior of liquids under high-frequency acoustic pressure. Frenzel and Schultes were using a tank of photographic developer fluid, a liquid bath of the kind used to develop photographic film. They were driving ultrasound through it, studying cavitation, studying the way high-frequency sound creates regions of low pressure in a liquid that cause bubbles to form, to oscillate, to collapse. And they noticed something they had not expected. The photographic film in contact with the liquid was becoming fogged. Not in patterns that corresponded to any image, not in ways that suggested the film was being exposed to light from an external source, but in tiny, scattered spots. Tiny marks of exposure distributed through the field where the bubbles were forming and collapsing. Light, the collapsing bubbles were producing light. Or at least, that is what they inferred. The film told them. The photographic process, which is exquisitely sensitive to light, far more sensitive than any eye in most conditions, had caught something that was happening in the fluid, something the researchers could not see directly, but that the film recorded with quiet fidelity. What Frenzel and Schultes had found was what is now called multi-bubble sonoluminescence, MBSL. Not a single trapped bubble. Not a controlled experiment with one spherical collapse repeating on a steady acoustic cycle, but a cloud of cavitating bubbles, dozens or hundreds or thousands of them forming and collapsing in the acoustic field. Each one briefly emitting light at the moment of its collapse, the whole ensemble producing a faint, diffuse, bluish glow that was hard to see with the naked eye, but that the photographic film recorded. This glow, the multi-bubble glow, was the beginning of the field. And it was real, it was reproducible, and it was completely unexpected. But it was also hard to study. A cloud of bubbles is chaotic. Individual bubbles form at different points in the acoustic cycle, collapse at different times, interact with each other, merge, split, migrate through the liquid. The light they produce is the sum of many individual events happening at slightly different moments and slightly different positions. And distinguishing the contribution of any single bubble from the rest is, to put it mildly, difficult. The multi-bubble case is noisy in every sense of the word, acoustically noisy, optically noisy, dynamically noisy. So for decades, multi-bubble sonoluminescence remained what it had been when Frenzel and Schultes found it, a genuine but puzzling laboratory curiosity. A glow that appeared when you drove ultrasound through water, faint and bluish and indistinct, hard to characterize, hard to explain in detail, hard to connect to any precise theory of what was happening inside any individual bubble. Research continued, gradually, in fits and starts. Over the decades following 1934, various groups investigated the effect, tried to understand the spectrum of the light, tried to measure its intensity, tried to connect it to the physics of cavitation. The connection to heating, to compression, to the violent final moments of bubble collapse, these ideas were in the air. Part of how physicists thought about what must be happening, but the chaos of the multi-bubble system made it nearly impossible to make precise measurements, to compare theory with experiment in a rigorous way. What the field needed was a single bubble, one bubble, perfectly spherical or close enough, trapped in a known location, collapsing at a known time on every cycle of the acoustic drive. Repeating its behavior reliably, steadily, for as long as the experiment ran, emitting its flash at a predictable moment, from a predictable place, again and again and again. If you had that, you could measure it, you could point detectors at it, you could analyze its spectrum, time its flash, study how its behavior changed when you varied the conditions. You could do real science. The leap to that single bubble happened in 1989 and 1990 at the University of Mississippi, and the person who made it happen was a graduate student named Felipe Gaitan. Gaitan was working under the supervision of Lawrence Crum, a physicist who had spent years studying acoustic cavitation and was deeply interested in understanding the precise mechanisms by which sound interacted with bubbles in liquid. Crum knew the multi-bubble field well. He knew its limits. He was interested in whether it might be possible to isolate and study a single sonoluminescing bubble in a way that had never been done before. Gaitan took on the problem in his doctoral research. The challenge was not conceptually mysterious, the physics of acoustic trapping, of how an acoustic standing wave can exert a radiation force on a small object and hold it at the pressure antinode, was understood in principle. But making it work in practice, for a bubble that needed to be small enough and stable enough to maintain single bubble behavior through thousands of collapse cycles, required careful experimental craft. The right liquid, the right frequency, the right drive amplitude, the right bubble size. And then there was the fact that nobody was entirely sure it could be done, or whether a single bubble could sustain stable sonoluminescence without splitting, or dissolving, or behaving in ways that would make it impossible to study. But Gaitan found it. He found the conditions, the degassed water, the acoustic frequency in the ultrasound range, the drive amplitude in that narrow stable window, the properly seeded gas, under which a single tiny bubble could be trapped at the antinode of a standing acoustic wave in a small flask, and would sit there, collapsing and re-expanding, emitting its pinprick of light on every acoustic cycle, stable and repeatable, and bright enough to see in a darkened laboratory. His 1990 doctoral thesis at the University of Mississippi is the standard point of origin for single-bubble sonoluminescence as a distinct and tractable field of study. Before Gaitan, sonoluminescence was the multi-bubble glow, interesting, genuine, but intractable. After Gaitan, it was a single point of light in a small flask, blinking 30,000 times a second, steady as a metronome, waiting to be measured. The difference between those two things, between a chaotic cloud of collapsing bubbles and one stable, isolated, precisely repeating event, is the difference between trying to study a single voice in a crowd and being in a quiet room with one speaker who says the same word, at the same volume, at the same time, over and over. The crowd tells you something. The single speaker tells you everything. And scientists could now listen. The work that followed Gaitan's breakthrough spread rapidly through the physics community. Experimental groups around the world, in the United States, in Europe, in Asia, began building their own SBSL setups, varying the conditions, making measurements, arguing over what the results meant. The small flask experiment is not difficult to reproduce in principle. The basic requirements are modest enough that it has been demonstrated in undergraduate teaching laboratories. What made the science difficult was not the apparatus itself, but understanding what the apparatus was producing. The interpretation of the spectra, the timing measurements, the question of what temperature meant inside a collapsing plasma too small and too fast to observe directly. Among the groups that drove the science hardest in these years was the group at UCLA. Seth Putterman, a physicist who had been thinking about the problem of energy focusing in cavitation for years, became one of the central figures in the field's rapid development after Gaitan's breakthrough. Bradley Barber, working with Putterman, produced some of the key early measurements of the flash timing. Those early results suggesting pulses of under 50 picoseconds, which set off the race to understand how a collapse of nanosecond dynamics could produce a flash so much shorter than the collapse itself. And in 1995, Putterman did something that brought the whole subject to a much wider audience. He published an article in Scientific American titled Sonoluminescence, Sound into Light. Scientific American is not a technical journal, it is a magazine for the broadly scientifically literate public. The kind of publication that sits on coffee tables in the homes of curious people. The kind that can take a result from a specialist field and explain it to anyone who wants to understand it. Putterman's article did exactly that. It described the trapped bubble, the supersonic collapse, the picosecond flash, the temperatures inferred. It described the strangeness and the wonder of what Gaitan had found, and what the subsequent years of work had revealed. And it gave the phenomenon a name that stuck. Star in a jar. The phrase is simple. It is, in some ways, almost too simple. It sounds like something from a children's science book, or from the promotional materials of a magic show. But it is also precise in its way. A star is a ball of hot plasma compressed by gravity, hot enough to glow. The thing in the flask is a ball of hot plasma compressed by sound, hot enough to glow. The physical processes are different: gravity versus acoustic pressure, stellar hydrogen burning versus the radiative cooling of a transiently heated gas, but the description of what you see is accurate. You see a tiny point of light, visible in a darkened room, sustained by forces that compress matter to stellar temperatures. Star in a jar is not hyperbole, it is a metaphor that earns its claim. The sound into light phrasing in the article's subtitle captures the other astonishing aspect of the phenomenon: the conversion of energy from one domain to another, from mechanical waves in a liquid to electromagnetic radiation, through the intermediate step of compressing a gas to plasma temperatures. Sound into light. The transformation has a kind of alchemical quality to it, a suggestion of something impossible becoming possible at the right conditions, in the right small flask, at the right frequency. Putterman's article reached people who were not physicists. It reached engineers and teachers and science writers and students in high school who found Scientific American in their school libraries. It reached people who would go on to do their own experiments, to set up their own small flasks with piezoelectric transducers glued to the glass, to look in a darkened room for the tiny, steady point of blue-white light that would tell them the bubble was there and glowing. And it seeded a period of intense scientific interest that brought many of the big questions into focus. If this is a plasma, and by the late 90s and early 2000s the spectroscopic evidence was building that it genuinely was, then what kind of plasma? At what temperature? By what process does a plasma formed in a collapsing bubble emit light? And is that emission the same as what a star does, or something subtly different? How far does the analogy go before it breaks down? These are the questions the field moved toward answering, and some of them have been answered, partly or provisionally. The plasma is real. We have seen that in the spectral lines, in the Flannigan and Suslick work in sulfuric acid, in the measured temperatures around 15,000 Kelvin with ionized species present. The emission is almost certainly thermal in character, driven by the extreme compression and heating of the gas. The broadband, featureless continuum that appears in water is consistent with the behavior of a hot, dense, partially opaque plasma. But the details, the exact mechanism in the final picoseconds, the true peak temperature at the center rather than the edge of the emitting region. The question of whether a converging shockwave plays a role in focusing energy further, or whether the hotspot thermal model is sufficient without shocks, these remain genuinely open. The field has converged on an outline. The center of the story is clear. But the fine grain of the physics, the exact path by which those last photons escape in the last tens of picoseconds of the collapse. That is still being worked out, and there was a chapter in this story that went somewhere much farther, much more dramatic, and ultimately much more cautionary. A chapter that shows how a real, genuine phenomenon, a bubble genuinely hotter than the sun's surface, a bubble producing a genuine plasma, can become the substrate for speculation that outstrips the evidence, and how the scientific community eventually, carefully, corrects course. That chapter begins with a question that must have occurred to anyone who took seriously the temperatures inside a sonoluminescing bubble. If the temperatures genuinely reach tens of thousands of degrees, or if the core might be hotter still, then what becomes possible? At stellar temperatures, certain atomic nuclei can fuse. Hydrogen fuses into helium in the cores of stars. Deuterium, a heavy isotope of hydrogen with an extra neutron, fuses at temperatures and pressures within the range that stellar interiors achieve. Could a collapsing bubble reach conditions hot and dense enough for nuclear fusion? It is not a crazy question. The temperatures at least reach the neighborhood of where fusion becomes thinkable, at the very low end. The pressures inside the collapse are extreme. If you could compress the right material to the right conditions in the right way, and if the conditions inside the bubble were more extreme than the directly measured values suggested, we will follow that question to where it led, and to what it taught the field about the difference between what a measurement shows and what speculation builds on top of it. But that is where part of the next stretch of this story goes. Before we get there, it is worth sitting for a moment with what the 1990s gave us and what Gaitan's single-trapped bubble and Putterman's popular account of it meant for the people who encountered this phenomenon for the first time. There is something that happens when you actually look at one of these experiments. You sit in a darkened room. There is a small flask on a table. It might be a round-bottomed flask or a cylindrical container filled with water that has been carefully treated, carefully degassed, carefully prepared. There are piezoelectric transducers glued to the outside of the glass, wired to an amplifier, wired to a signal generator. The signal generator is producing a tone in the ultrasonic range, above human hearing, a frequency that makes the water in the flask resonate in a standing wave pattern, like a note held steady on a tuning fork pressed to the glass. You cannot hear it, but you can see what it does. There, at the center of the flask, at the pressure antinode, the point where the acoustic standing wave holds maximum pressure variation, there is a point of light. Steady and small and very blue, like a tiny star hovering in the water. Not flickering or not appearing to flicker, because it blinks 30,000 times a second and persistence of vision makes it look continuous. But in fact, it is a rapid, steady pulse, each pulse lasting only a fraction of a nanosecond, each one representing a single cycle of the driving sound, the expansion, the collapse, the plasma flash, the re-expansion, the next cycle. It just sits there, quietly, in the middle of the water. People who have seen it describe it as remarkable in a particular way. Not dramatic, not explosive, not the way you might imagine something hotter than the sun would look. It is small. It is calm in its visual effect. It looks like a single pixel of light caught in a jar, and you could be forgiven for not immediately grasping what it represents. But what it represents is this, that inside that still point, 30,000 times every second, a bubble is collapsing faster than sound, reaching temperatures higher than the surface of the star 8 minutes away from this planet, and emitting a flash of light so brief that it takes a roomful of sophisticated electronics to measure its duration. Still, steady, quiet-looking, and genuinely extraordinary, in a way that only reveals itself when you start to think about the numbers. And yet the numbers are not the only thing worth sitting with tonight. Because there is a thread running under all of this, under the bubble and the plasma and the picosecond flash, a thread that connects this small, quiet jar of water on a benchtop to something much older. Something that happened long before anyone had built a piezoelectric transducer or a signal generator, or even thought to ask what sound might do to a bubble in the dark. The thread goes back to 1917, and to a mystery involving the Royal Navy, Lord Rayleigh, John William Strutt, the third Baron Rayleigh, Nobel laureate, one of the great systematic physicists of the 19th and early 20th centuries, turned his attention in 1917 to a problem that had been quietly frustrating the British Admiralty for years. The problem was propellers. Specifically, the fact that the propellers on fast naval vessels were being destroyed, not by enemy action, not by running aground, but by the water itself. The blades came out of service, pocked and pitted, eaten away as though something had been chewing on the metal. Staring, one of the torpedo boat destroyers of the era, was a particular case. Engineers were mystified. The water was doing something to the steel that no one could quite account for. What it was doing was cavitation. When a propeller blade moves fast enough through water, the pressure on the low-pressure side of the blade can drop so sharply that it falls below the vapor pressure of water, the point at which water, even at room temperature, spontaneously boils. Not because it's hot, because the local pressure has plummeted so far that liquid water becomes unstable and bubbles of water vapor appear. They form in the low-pressure zone behind the blade, get swept along with the flow, and then, when they reach a region of higher pressure, they collapse. Violently, the pressure difference drives the surrounding liquid inward with enormous force. And the bubble doesn't just pop gently like a soap bubble in the air, it implodes. The center of the bubble experiences, briefly, a convergence of kinetic energy that produces extraordinary local temperatures and pressures. And when that converging wall of liquid hits the metal surface of the propeller, it hits it like a hammer, many thousands of times per second per square centimeter of blade surface. Over time, the metal fatigues and fractures, and you get a pitted, cratered, weakened blade. Rayleigh worked out the mathematics of this in 1917, the collapse of a spherical void in an incompressible liquid. It was a clean, elegant piece of analysis. He assumed a spherical cavity, an incompressible surrounding fluid, and asked, how does the radius evolve as the cavity collapses under external pressure? The answer came out in a form that would later be named the Rayleigh-Plesset equation, extended by others over the following decades to account for viscosity, surface tension, the compressibility of the liquid at high velocities, and the behavior of the gas trapped inside. But the essential physics, the way a converging spherical collapse focuses pressure and energy into a diminishing volume, was Rayleigh's. The same equation that describes the destruction of those naval propellers describes what is happening inside that small flask on a benchtop today. That is not a metaphor. That is the literal mathematical truth. When Gaitan and Crum trapped their single bubble and drove it through its violent acoustic cycle, the physics governing the collapse was descended directly from Rayleigh's 1917 analysis of the staring problem. The ore of sonoluminescence has deep engineering roots. It is, in a very real sense, the light produced by the same force that chews up warships. Cavitation is still, in the 21st century, a major engineering headache. Pump impellers, ship propellers, hydrofoils, wherever fast-moving liquid encounters a sudden pressure change, cavitation can occur, and wherever cavitation occurs, metal erodes. The pitting patterns on pump blades look almost identical to the pitting patterns that puzzled the British Admiralty more than a century ago. Engineers spend considerable effort designing around it, shaping blades, managing flow, choosing materials. It is destructive, and it is real, and it is not exotic at all. It is ordinary physics operating at ordinary scales of velocity and pressure. But in a carefully controlled acoustic trap, at the precise tuning of frequency and amplitude and dissolved gas content that Gaitan found, the same collapse is not destroying anything. It is producing light, the same converging implosion, the same focusing of pressure into a shrinking sphere, but now held perfectly still at the pressure antinode of a standing wave, perfectly synchronized, repeating without deviation tens of thousands of times a second. The violence is real, the temperatures and pressures are real, and yet the whole thing is stable and small and sits quietly in a jar. That stability itself is part of what makes sonoluminescence so scientifically useful, and it is also part of what makes the central mystery so sharply defined. Because here is where we have to be honest about something. There is a part of this that everyone agrees on. And there is a part of this that nobody has fully settled. Those two parts are distinct, and it matters to be clear about which is which, because a great deal of what you will find written about sonoluminescence in popular accounts blurs them together in ways that are not quite accurate in either direction. Some accounts make it sound more mysterious than it is. Others make it sound more understood than it is. The truth is somewhere more interesting than either extreme. The part that is settled, or very nearly so, is the large-scale physics of the collapse. The acoustic trap, the expansion cycle, the supersonic inward rush of the bubble wall, the near adiabatic compression of the trapped gas, the formation of a hot, partially ionized plasma. All of this is supported by solid experimental evidence and well-tested theory. The 1917 Rayleigh analysis, refined by the Rayleigh-Plesset equation, gives you the gross dynamics of the collapse in good quantitative agreement with measurements. The temperatures of roughly 15,000 Kelvin detected by Flannigan and Suslick in their 2005 Nature paper, the ionized argon, the ionized oxygen, the spectral lines of a real plasma, those are direct measurements. The argon rectification hypothesis of Lohse and Brenner and Hilgenfeldt, explaining why the bubble concentrates its inert gas content, is supported by the observed behavior of different gas species. The picosecond timing of the flash, measured by Gompf and colleagues in 1997 with time-correlated single-photon counting, is as solid as any measurement in the field. These things are not in dispute. What is in dispute, genuinely, actively, among working physicists, is something more specific. It is the question of exactly how, in the last bright fraction of that final collapse, the light is produced. The precise mechanism of the emission, and connected to that, the question of just how hot the very center of the bubble actually gets. Let me try to explain why those two questions are still open. Because the reason is itself interesting. When you measure the spectrum of the light from a sonoluminescing bubble, the distribution of its intensity across different wavelengths, what you find in ordinary degassed water is a broad, featureless continuum. No sharp peaks, no clean emission lines, just a smooth hump of intensity that rises toward the ultraviolet and then disappears. Not because the intensity actually drops there, but because the water absorbs ultraviolet light before it can get out. The true peak of the spectrum is hidden. You cannot see it directly. And that featureless continuum is consistent with several different emission mechanisms, which is exactly why the debate has persisted. The first and oldest candidate is the hotspot thermal model. The gas inside the bubble is compressed nearly adiabatically, meaning so fast that it cannot shed heat to its surroundings during the compression, and it gets extremely hot. A hot, dense gas emits thermal radiation. If the temperature is high enough, the spectrum of that radiation is broad and roughly follows the shape of what physicists call a blackbody spectrum, or something close to it. The featureless continuum from the bubble looks, at first pass, something like a blackbody spectrum from a very hot object. The argument, in its simplest form, is that you have compressed hot gas, and hot gas glows. This is not a wrong argument, but it is an incomplete one. A true blackbody emitter requires the gas to be optically thick, dense and opaque enough that radiation is absorbed and re-emitted many times before it escapes, which is what gives a blackbody spectrum its smooth, featureless shape. Whether the bubble at peak compression is actually optically thick across the spectrum, or just partially so, is part of the argument. The second candidate is Bremsstrahlung, a German word that translates, roughly, as breaking radiation. When free electrons are decelerated by their interactions with ions in a plasma, they emit radiation. A hot plasma, with its mix of free electrons and positive ions, naturally produces Bremsstrahlung across a broad range of wavelengths. The spectrum of Bremsstrahlung emission is also broad and continuous, rising toward shorter wavelengths at the temperatures involved. Suslick's spectroscopic work showing ionized species inside the bubble, a genuine plasma at around 15,000 Kelvin, suggests that Bremsstrahlung is at least part of the story. A plasma is the right kind of object to produce Bremsstrahlung, and the numbers are at least roughly consistent with the observed light intensity and spectral shape. But Bremsstrahlung from a plasma at 15,000 Kelvin, while certainly plausible, may not fully account for all the observations either, particularly the shortest and brightest flashes seen in extreme conditions. The third candidate is more dramatic. It is the converging shockwave model, developed by Wu and Roberts. Their argument is that the collapse of the bubble does not stop at simple adiabatic compression. Instead, as the bubble wall rushes inward supersonically, it launches a converging spherical shockwave into the gas inside the bubble. A converging shock is a remarkable thing. As it moves inward, it is focusing energy into a steadily shrinking volume. In the limit, a perfectly spherical converging shock would focus an infinite amount of pressure at the center, though in practice various physical effects prevent that singularity. But even a partial focusing, a converging shock that does not quite reach the mathematical ideal, concentrates energy at the center of the bubble to a degree that far exceeds what simple adiabatic compression alone would produce. In the Wu and Roberts picture, there is a very small, very hot core at the very center of the bubble, hotter than the surrounding emitting shell, possibly much hotter. And it is this core that produces the brightest, most extreme emission. This is why the question of the true peak core temperature is so hard to answer. If the converging shock hypothesis is correct, or partially correct, then the measured temperatures from spectroscopy, the 15,000 Kelvin from Flannigan and Suslick, represent the temperature of the outer emitting shell of the plasma, the part that is optically thin enough for light to escape. The inner core, if it exists, would be optically thick. It would absorb radiation before it could get out, and you would have no direct spectroscopic access to it at all. The bubble hides its hottest secrets behind its own opacity. The light you measure comes from the surface of the radiating region, not from the center, just as the light you see from the sun comes from the photosphere, the sun's visible surface, and tells you very little directly about the temperature at the solar core. This is one of the genuinely open questions in the field, and it is worth saying slowly, we do not know the temperature at the center of the collapsing bubble. We have measured the temperature of the outer emitting region with good spectroscopic evidence, roughly 15,000 Kelvin. A real plasma, a number that is already extraordinary. But whether a converging shock exists and what it does to the very center remains a matter of active theoretical and experimental debate. Some hypotheses place the core temperature far higher, tens of thousands, conceivably more, while remaining consistent with the measured outer temperature. How much higher is genuinely unknown, and the picosecond duration of the flash adds another layer of difficulty. 50 to 250 trillionths of a second. That is how long the brightest part of the emission lasts. Even with excellent instruments, even with the kind of time-correlated single-photon counting apparatus that Gompf and colleagues used in 1997 to pin down the flash width. 50 picoseconds is extraordinarily fast. It is fast enough that the detailed time evolution of the emission during that window is very hard to resolve. You would like to know, for instance, whether the flash has a particular temporal shape that would distinguish a simple thermal burst from a more complex, shock-focused emission. But extracting that information from light, pulses this brief, requires instruments at the very edge of what can be built. The measurement is hard, and the signal is small. Remember, each flash is only 100,000 to 1,000,000 photons, and the experimental uncertainties are not small. So this is where the field actually is. The big picture is clear. The detailed mechanism of the final, brightest phase of the emission is not. 3 models, each with supporting evidence, each with difficulties. A featureless spectrum that is consistent with more than one mechanism. An optically thick inner core that may be far hotter than anything measured, or may not exist in the dramatic form the shock model suggests. An emission timescale so brief that distinguishing between the models requires measurements at the frontier of instrumentation. That is not a failure of science. That is science at work on a genuinely hard problem. The honest framing is this. We understand the large-scale physics of sonoluminescence well. We can calculate the bubble dynamics. We can predict when a bubble will be stable and when it will break up. We can explain why argon makes the light brighter, why cold water works better than warm water, why the flash is so precisely timed. What we cannot yet do is peer into the last 50 picoseconds of the collapse with enough resolution to say with certainty which emission mechanism dominates, or how hot the very center actually gets. Those questions are real, bounded, specific, and they remain open. It is worth knowing this, not because it diminishes what sonoluminescence is, but because it explains why physicists are still working on it. You do not spend decades studying something that is already fully solved. The reason this phenomenon continues to attract careful experimental and theoretical attention is precisely that the answer to a well-defined question, how does this plasma emit its light, is still not definitively in hand. Now, there is one more chapter to this story, and it is a cautionary one. a chapter about what happens when a genuine and extraordinary phenomenon meets the understandable human desire to believe that something extraordinary means something even more extraordinary than it actually does. In 2002, a paper was published in the journal Science. The lead author was Russi P. Argon, then a physicist at Oak Ridge National Laboratory. The paper claimed something remarkable, that acoustic cavitation in deuterated acetone, a variant of ordinary acetone in which the hydrogen atoms had been replaced by deuterium, a heavier isotope of hydrogen, produced not just sonoluminescence, but actual nuclear fusion. The claim was that neutrons were being emitted from the collapsing bubbles, and that tritium was being produced inside them. If true, this would have been extraordinary. Deuterium-deuterium fusion is the kind of fusion that produces neutrons and tritium. If a collapsing bubble in a laboratory flask was actually achieving fusion temperatures in the range of tens of millions of Kelvin, far beyond even the highest estimates for ordinary sonoluminescence, it would have been one of the most significant results in nuclear physics in decades. The paper called it bubble fusion. Others called it sonofusion. And for a time, it attracted enormous attention, not just in the scientific press, but in the broader public imagination. Here, some articles implied, was the long-sought desktop fusion reactor. Here was the promise of clean energy from a jar of liquid on a benchtop. The Ark of Hope was familiar, a small, cheap tabletop experiment producing something that enormous and expensive machines had failed to achieve. But the results did not hold up. The key test in science is independent reproduction. Other groups, with independent equipment and no stake in the outcome, attempted to reproduce the neutron emission and the tritium production. They did not find it. Multiple careful, well-equipped groups looking for the same signal found nothing. The experimental conditions were scrutinized, the data analysis was questioned. A subsequent examination by a panel convened by Purdue University, where Argon had moved, concluded in 2008 that there were serious problems with the work, including findings of research misconduct. The story of bubble fusion became, over the course of those years, not a story about a new energy source, but a story about the difficulty of extraordinary claims, the pressures that can distort scientific judgment, and the importance of the independent replication that is supposed to be, and in this case ultimately was, science's self-correcting mechanism. None of this changes sonoluminescence itself. The effect is real. The plasma is real. The temperatures of 15,000 Kelvin or so, extraordinary by everyday standards, though nowhere near the tens of millions of Kelvin needed for fusion, are real, and they are genuinely impressive on their own terms, without needing to be anything more than they are. The problem was not with the bubble. The problem was with the leap. The assumption that because something is extreme, it must be even more extreme than the measurements show. That because a bubble produces temperatures hotter than the sun's surface, it must produce temperatures high enough for fusion. The measured temperatures and the fusion temperatures are separated by a factor of roughly 1,000. That is not a small gap. It is a useful episode to know about. Not to diminish sonoluminescence, but to understand it more clearly. The phenomenon is genuinely astonishing without the fusion story. A repeatable bench-scale plasma, hotter than the solar photosphere, made with a flask and a signal generator, glowing 30,000 times a second in tap-clear water, that is already a thing that should make you stop and look at the world slightly differently. It does not need to be a fusion reactor to be worth thinking about. And the sonofusion episode is a good reminder of something that science as a practice keeps relearning. The most reliable path to wonder is accuracy, not amplification. So let's just sit with what it actually is for a moment. There is a flask of water, cold, still, carefully degassed, perhaps sitting on a bench under a lamp in a lab somewhere, or perhaps in an undergraduate teaching laboratory being set up right now by a student who read about this and wanted to see it for themselves. There is a signal generator, a small amplifier, 2 piezoelectric transducers pressed to the glass. Someone turns on the power, and the sound begins, not loud, not audible to the ear in a meaningful sense, just a steady hum of electricity driving the glass into vibration at around 20 or 30,000 cycles per second. And somewhere in the water, a small air bubble, seeded perhaps with a bit of noble gas, finds the pressure antinode and locks in. And then it begins its cycle, expanding slowly as the pressure drops, growing to perhaps 50 micrometers, roughly half the width of a human hair, then contracting, first gently, then faster, then suddenly, catastrophically fast, the bubble wall accelerating to supersonic speeds in the final nanoseconds, the gas inside being compressed in a fraction of a microsecond to a temperature of many thousands of Kelvin, the whole interior briefly becoming a tiny plasma of ionized atoms, and then the flash. One flash, lasting perhaps 100 trillionths of a second, emitting perhaps 500,000 photons. Then the re-expansion, the afterbounces, the settling. And again, and again, and again, 30,000 times every second. And from outside it looks like a single steady pixel of blue-white light hovering in the center of the flask. Still, undemanding, you could walk past it and not know what you were looking at. But you know now. You know that the light you would see, if you were looking at it right now, is the sum of those flashes, each one brief, beyond easy imagining. Each one the product of a supersonic implosion. Each one a tiny, real, measured plasma hotter than the visible surface of the sun. You know that the bubble making those flashes has been slowly eating its own reactive gases over thousands of cycles, concentrating its inert argon until it is, effectively, a pure argon plasma at peak compression. You know that the mathematics underlying its collapse were worked out a century ago by Lord Rayleigh, trying to understand why warship propellers were being destroyed by the sea. You know that measuring the duration of those flashes required some of the most sensitive light detectors ever built. You know that the precise mechanism producing the light, whether it is purely thermal emission from a hot dense gas, or Bremsstrahlung from a plasma, or the focused intensity of a converging internal shock wave, or some combination of all three, is still being argued about in the physics literature. And you know that scientists have been making this thing reliably, reproducibly, on benchtops around the world for more than 3 decades. There is something that I find quietly remarkable about all of that. Not in a way that demands any particular response from you, not in a way that calls for excitement or urgency, just quietly remarkable. The way certain things are when you look at them from the right angle. We are, as a species, in the habit of imagining that the extremes of nature live far away, at the cores of stars, at the centers of black holes, in the first microseconds after the Big Bang. In places that are, by definition, inaccessible to us, places we can only study indirectly, places whose conditions we can only infer from the light and particles they send outward across vast distances. And there is something true in that habit. The heart of the sun is genuinely not here. But sonoluminescence is a small, precise reminder that the extremes of physics are not always distant. Sometimes they are available in a flask of cold water, with a few transducers and a signal generator, in a room that also contains a coffee maker and a whiteboard covered with equations. Sometimes a process that produces temperatures exceeding the solar photosphere is something a physics undergraduate can set up in an afternoon lab session. Sometimes the frontier of human knowledge is not in space or at the bottom of the ocean, but in a bubble smaller than a grain of salt, hovering in a small flask on a desk, blinking in the dark. And the part that is still unknown, the true mechanism of those last bright picoseconds, the temperature at the hidden center of the plasma, is not a failure to understand. It is the current edge of understanding. The place where the measurements are genuinely hard, where the instruments are being pushed to their limits, where the theoretical models are still being tested against new experimental results. Every scientific field has an edge like this. Sonoluminescence's edge happens to be very small and very fast and very hot. It happens to involve a physical process that compresses into a volume far smaller than the period at the end of this sentence, in a time far shorter than the interval between one heartbeat and the next. And it happens to be visible, in principle, to the naked eye, a small blue pixel of light in a flask of water, available to anyone who puts the apparatus together correctly and gets the conditions right. That visibility matters, I think. There is something different about a phenomenon you can see, even if what you see gives you no direct sense of what is happening at the scale of the physics. You can look at that point of light and know, without being able to perceive it directly, that inside it, right now, something hotter than the sun's surface is happening and ending and happening again, 30,000 times a second. The seeing and the knowing are separate. The light reaches your eye as a calm, steady, small thing. The knowledge reaches your mind as something else entirely. Wherever you are listening from tonight, whatever corner of the world you are in, whatever hour it is, whether there is a lamp still on or the room is dark, I want to gently point out something. The atoms in your body, right now, are subject to the same fundamental physics that drives that bubble. The same quantum mechanical interactions between electrons and nuclei, the same electromagnetic forces, the same thermodynamic principles that govern how energy flows from a hot object to a cold one. You are not separate from the physics of a sonoluminescing bubble. You are, in a very literal sense, made of the same stuff, governed by the same rules. The difference between a plasma at 15,000 Kelvin and the comfortable temperature of a human body is a difference of scale and arrangement, not a difference of kind. Your atoms have been in hot places before, not you, not in this form. But the carbon and oxygen and nitrogen and hydrogen that make up the molecules that make up your cells have travelled long paths through the universe. They were forged in stellar interiors at temperatures that make that little plasma flash look modest. They were scattered by stellar deaths, gathered by gravity, incorporated into planets and oceans, and eventually into the chemistry of life. They carry, in their nuclei and their electron configurations, the record of processes far more violent than anything a benchtop experiment can produce. You are, if you want to think about it that way, a very cool, very organized, very improbable arrangement of atoms that have seen much hotter days. And you are, right now, lying or sitting somewhere quiet, perhaps with a blanket nearby, perhaps with a light that's getting softer, perhaps already half in the country between waking and sleep. And somewhere in a physics laboratory, perhaps still lit, perhaps locked up for the night, there is a flask of cold degassed water with 2 transducers pressed to its glass. And if the power is on, somewhere in that flask, a bubble smaller than a grain of salt is collapsing and glowing and collapsing and glowing 30,000 times a second, patient and precise and entirely indifferent to whether anyone is watching. The star in a jar keeps doing what it does, whether or not the lights are on, whether or not anyone is in the room to see the small blue pixel of it, whether or not the debate about its exact emission mechanism has been resolved yet. It keeps collapsing. It keeps glowing. It keeps waiting, in its way, for someone to understand it 1 degree more completely than it has been understood before. That seems to me like a good thing to carry into sleep. The idea that the universe's most extreme processes are available, in miniature, in a flask of water, that the questions science has not yet answered are specific and bounded, not vast vague mysteries, but precise, named, measurable puzzles with researchers actively working on them. That the line between the known and the unknown in any given field is not a wall, but a frontier, and the frontier of sonoluminescence is a very small, very hot, very fast, very beautiful place. If you have drifted off somewhere along the way, and that would be entirely fine, this is after all what we came here for, then the bubble is still there in your sleep. Still collapsing 30,000 times a second in some laboratory somewhere, still producing its trillionth of a second spark. You can catch up with the mechanism debate another time. It will still be unresolved in the morning. And if you are still here, still following the thread, thank you for staying with it. For sitting with the Rayleigh, Plesset equation and the Hms-Daring and the argon, rectified plasma and the picosecond flash. It's a lot to hold gently in the mind just before sleep, and you have held it well. If you enjoyed drifting through this slow journey tonight, a gentle like or subscribe means a great deal. Small creators like me rely on your support to keep these nights going. And do tell me, if you feel like it, where in the world you are listening from and what time it is in your corner of the night. Those little coordinates always make me smile. The thought of all the different darknesses and lamplight pools and quiet rooms where someone is listening. Until next time, and there will be a next time, another slow journey into something strange and real and quietly wonderful, I'll leave you with the image of that small blue pixel in its flask. Steady, patient, ordinary looking. And on the inside, hotter than the sun. Sleep well, fellow voyager. The next journey keeps until you wake.